Welcome! Today, we'll be exploring LeetCode problem number 224, titled Basic Calculator. This problem challenges us to evaluate mathematical expressions represented as strings, which may contain integers, operators, and parentheses. We'll analyze the problem, discuss different approaches, and break it down step by step. Let's dive in. In this problem, we are tasked with implementing a basic calculator to evaluate a given string S that represents a valid mathematical expression. This expression can include digits from 0 through 9, two operators, addition represented by plus and subtraction represented by dash, parentheses to manage operation precedence, and spaces which should be ignored during evaluation. The problem guarantees that the input string is valid, meaning it contains no invalid characters and follows the specified rules. The goal is to compute and return the result of the expression as an integer. The input to the problem is a string S with a length that ranges from 1 to 300,000 characters. This string may include digits, the plus and dash operators, parentheses for grouping, and spaces that don't affect the computation. The output of the problem is a single integer representing the evaluated result of the expression. Let's look at some examples to better understand how the calculator should work. For instance, if the input string is S equals 1 plus 1, the expression evaluates to 2 because adding 1 and 1 gives us the result of 2. Now consider another example where the input string is S equals 2 to 1 plus 2. In this case, spaces in the string are ignored during evaluation, so the expression simplifies to 2 1 plus 2. Performing the operations from left to right, we subtract 1 from 2 to get 1, then add 2 to achieve the final result of 3. Here's another example involving parentheses, S equals 1 plus 4 plus 5 plus 2, dash 3, plus 6 plus 8. Parentheses are used to group operations, so the expression must be evaluated step by step to get the correct result. Breaking down the evaluation of the expression, 1 plus 4 plus 5 plus 2, dash 3, plus 6 plus 8, we first handle the innermost parentheses. Within 4 plus 5 plus 2, adding 4, 5, and 2 gives 11. Next, we evaluate the outer parentheses, where 1 plus 11 3 results in 9. Finally, we compute the last addition, 9 plus 6 plus 8, which equals 23. The result of the entire expression is therefore 23. This example illustrates how parentheses can be nested and how their grouping affects the order of operations. To summarize, the problem comes with some important constraints. The length of the input string ranges from 1 to 300,000 characters, and it consists only of digits, the plus and dash operators, parentheses, and spaces. The expression is guaranteed to be valid, and all intermediate results will fit within a 32-bit signed integer. Parentheses can be nested arbitrarily, and spaces in the input must be ignored during evaluation. Operations are performed from left to right unless parentheses dictate otherwise. With these rules in mind, our task is to design an efficient solution that handles large inputs while maintaining correctness. When solving LeetCode problem number 224, the basic calculator, the main challenge lies in parsing a string that contains numbers, operators like plus and dash, and parentheses, all while maintaining the correct order of operations. One approach we could consider is a brute force method, where we traverse the string and evaluate the expression step by step. This might involve manually converting substrings into numbers, applying operators, and recursively evaluating sub-expressions within parentheses. However, this approach has several drawbacks. Managing parentheses explicitly can easily lead to errors due to the complexity of keeping track of nested expressions. Additionally, without using a structured way to store intermediate results, like a stack, it becomes difficult to manage the state of the computation effectively. This method also tends to have a higher time complexity because it repeatedly parses substrings and recalculates intermediate results, making it less efficient overall. A more efficient method for solving this problem is to use a stack-based solution. This approach is inspired by how a traditional calculator processes input, breaking the expression into smaller, manageable parts. As we traverse the string, we handle numbers immediately, applying the plus or dash operators to update a running total. When we encounter an opening parenthesis, we push the current result and the current sign onto the stack, isolating the sub-expression that follows. When we encounter a closing parenthesis, we pop the stack to combine the result of the sub-expression with the previous state. This takes advantage of the stack's ability to naturally manage the nesting introduced by parentheses. Key to this approach is tracking the current operator as either +1 or -1, ensuring that numbers are added or subtracted correctly. Additionally, by processing the string in a single traversal and using the stack to manage intermediate results, we achieve a clean, iterative solution that avoids the inefficiencies of recursion. An alternative approach, such as converting the expression into postfix notation, might seem simpler conceptually but requires extra processing in space, making it less efficient compared to this direct stack-based evaluation. The stack-based solution is our chosen strategy for this problem because it offers the best balance between efficiency, simplicity, and reliability. By processing the string in a single pass, this approach achieves a time complexity of O(n), while the stack ensures that we can manage intermediate states with space complexity proportional to the depth of nested parentheses. This makes it both time-efficient and space-efficient. The algorithm is also straightforward to implement, avoiding the overhead of recursion or the additional complexity of converting the expression into postfix notation. However, there are trade-offs to consider. While the stack uses memory proportional to the nesting depth, which could be significant for deeply nested expressions, this is generally manageable in most cases. Additionally, careful handling of operators and intermediate results is required to avoid introducing edge cases, but the structure of the solution helps mitigate these risks. The key insight here is recognizing that a stack naturally mirrors the nested structure of parentheses, allowing us to isolate and evaluate each sub-expression independently. By combining these results incrementally, we ensure correctness and efficiency, making this approach the optimal choice for the problem. In this problem, we're tasked with evaluating a mathematical expression represented as a string. The expression might include integers, the addition and subtraction operators, and parentheses, which define precedence. Spaces in the input string should be ignored, so they don't interrupt the parsing. The goal is to compute the final result by following standard mathematical rules, such as handling parentheses to prioritize certain operations and applying addition and subtraction correctly. This problem is particularly interesting because it requires us to process the string efficiently while managing nested structures and operator precedence. To solve this problem, we use a stack-based approach, which is well suited for handling the nested structure created by parentheses. First, we pre-process the input by removing all spaces to simplify parsing, leaving us with only the meaningful characters. Then, we initialize a few key variables, a stack to keep track of the computation state when dealing with nested parentheses, a variable current_sum to store the ongoing computation outside of parentheses, and a assign variable set to +1 or -1 to apply addition or subtraction. We also use an index variable to iterate through the string. As we process the string character by character, we classify each character into one of several categories: digits, operators, or parentheses. Each type requires a specific handling strategy to ensure the computation is accurate. When we encounter a digit, we parse the entire number, including multi-digit values, and update current_sum by adding the number multiplied by the current sign. For example, in the expression 12 plus 34, parsing the number 12 sets current_sum to 12. For operators like plus and dash, we update the sign to either +1 or -1, which ensures that the next number is added or subtracted correctly. When we encounter an opening parenthesis, we save the current computation state onto the stack, including current_sum and sign, and then reset both current_sum and sign to handle the new sub-expression inside the parentheses. For a closing parenthesis, we pop the saved state from the stack, adding the current_sum of the sub-expression to the previously saved current_sum. This process ensures that each nested calculation is correctly integrated into the overall result. At the end of the iteration, the current_sum variable contains the final result of the expression, which we return as the output. The stack is essential for managing nested parentheses, allowing us to save and restore the computation state as we enter and exit different levels of the expression. Using +1 and -1 for the sign value makes it straightforward to apply addition and subtraction without directly modifying the numbers themselves. Parsing numbers character by character allows us to handle multi-digit values efficiently without requiring extra parsing logic. By pre-processing the string to remove spaces, we avoid unnecessary checks during iteration, keeping the algorithm clean and focused. The combination of these techniques enables us to evaluate the expression accurately and efficiently. The time complexity of this solution is O(n), where n is the length of the string. Each character is processed exactly once, making the algorithm linear in time. The space complexity is also O(n), in the worst case due to the stack, which grows with the depth of nested parentheses in the expression. Several edge cases must be considered to ensure correctness. For example, an empty string or a string containing only spaces should return 0. If the input contains a single number, that number should be returned directly. For deeply nested parentheses, proper stack management is crucial to avoid errors. Finally, we assume that the input string is valid as per the problem constraints, so no additional validation for invalid input is required. These considerations ensure that the algorithm handles all scenarios effectively and efficiently. Here, we define the calculate function within the solution class. This function takes a string s as input and evaluates its mathematical expression. We start by initializing 4 variables: stack to keep track of results and signs when encountering parentheses, operand to build numbers from consecutive digits, result to store the ongoing calculation, and sign to track whether the current number should be added or subtracted. Then, we iterate through each character in the string s. If the character is a digit, we update operand by multiplying the current value by 10 and adding the integer value of the digit. This allows us to handle multi-digit numbers. If the character is a plus sign, we add the value of operand to result, applying the current sign, then reset operand to 0 and set sign to 1 for addition. Similarly, if the character is a minus sign, we update the result with operand times sign, reset operand, and set sign to -1 for subtraction. When encountering an opening parenthesis, we store the current result and sign on the stack, then reset result and sign to handle the new sub-expression. For a closing parenthesis, we first add the last operand to result with the current sign, then multiply the result by the last sign popped from the stack and add the previous result from the stack. This ensures that sub-expressions are evaluated correctly within the scope of parentheses. After processing all characters in the string, we handle any remaining value of operand. Since the loop does not automatically add the last number to result, we combine sign and operand to finalize the computation. Finally, the function returns the total result, which represents the evaluated value of the input mathematical expression. This implementation efficiently handles integers, addition, subtraction, and parentheses by using a stack to manage contexts within nested expressions. The overall approach is simple yet robust for parsing and calculating valid arithmetic strings. Here, we begin the implementation of the calculate method in Java, which evaluates a given arithmetic expression string. To start, we declare a stack to help us handle nested operations. We also initialize 3 variables: operand, result, and sign. The operand will store the current number being processed, result will store the cumulative calculation, and sign tracks whether the current operation is addition or subtraction. We then loop through each character in the input string. When we encounter a digit, we update the operand by multiplying the current value by 10 and adding the numeric value of the character. This accounts for multi-digit numbers. If the character is a plus sign, we add the last operand to the result, applying the appropriate sign, reset the operand to 0, and set the sign to positive. Similarly, if we encounter a minus sign, we add the operand to the result, reset the operand, and update the sign to negative. For an open parenthesis, we push the current result and sign onto the stack. This allows us to save the current state and start evaluating the expression inside the parentheses. Then, we reset result to 0 and set the sign to positive to handle the new scope. When a closing parenthesis is encountered, we first finalize the computation for the expression inside the parentheses by adding the current operand to the result, applying the current sign. Then, we pop the last sign from the stack and multiply it with the result. This step applies the sign that was active before the opening parenthesis. After that, we pop the previous result from the stack and add it to the current result, effectively combining the inner expression's result with the outer one. Finally, we reset the operand to 0 to prepare for the next calculation. Once the loop is complete, we return the cumulative result, including any remaining operand multiplied by its sign. This ensures the method handles cases where the expression ends with a number. This implementation efficiently handles nested expressions using a stack and maintains clarity by processing each character sequentially. To solve this problem, we start by initializing our variables, an empty stack, the operand set to 0, the result also set to 0, and the sign initialized to 1, which represents a positive number. Now, as we process the input string 1 plus 1, the first character is 1, which is a digit. Using the formula, operand *10 plus int character, we calculate the operand as 1. When we encounter the space, we simply skip over it. Next, we process the plus character, which indicates an addition operation. At this point, we add the current operand, multiplied by the sign, to the result. This gives us result equals 0 plus 1 by 1 equals 1. After that, we reset the operand back to 0 and keep the sign as 1, since the plus symbol represents a positive number. Skipping another space, we reach the final character 1, which is once again a digit. Using the same formula, the operand becomes 1 again. At the end of the string, we add the final operand, multiplied by the sign, to our result. This gives us result equals 1 plus 1 by 1 equals 2, which is the correct output for the expression 1 plus 1. Now, let's look at a slightly more complex example, the input string 2 to 1 plus 2. We start with the same initialization, an empty stack, operand is 0, result is 0, and sign is 1. The first character is 2, a digit, so the operand becomes 2. When we encounter the dash character, we add the current operand, multiplied by the sign, to the result. This gives us result equals 0 plus 1 by 2 equals 2. Then, we reset the operand to 0 and set the sign to -1, indicating a subtraction operation. Next, we process the character 1, which is a digit, so the operand becomes 1. When we encounter the plus character, we again add sign asterisk operand to the result, which now becomes result equals 2 plus -1 asterisk 1 equals 1. After this, we reset the operand to 0 and set the sign back to 1 for addition. The next character is 2, which is a digit, so the operand becomes 2. At the end of this string, we add sign asterisk operand to the result. This gives us result equals 1 plus 1 by 2 equals 3, which is the correct result for the expression 2 to 1 plus 2. Now, let's explore a more complex example, the input open parenthesis 1 plus open parenthesis 4 plus 5 plus 2 close parenthesis minus 3 close parenthesis plus open parenthesis 6 plus 8 close parenthesis. We begin with our usual initialization, an empty stack, operand is 0, result is 0, and sign is 1. The first character is, so we push the current result and the sign onto the stack. This is done to save the context of the outer expression. At this point, the stack becomes 0, 1. Then, we reset the result to 0 and the sign to 1. The next character is 1, which is a digit, so the operand becomes 1. When we encounter the plus character, we add sign asterisk operand to the result, which gives us result equals 0 plus 1 by 1 equals 1. After this, we reset the operand to 0 and keep the sign as 1. The next character is another, so we again push the current result and sign onto the stack. This time, the stack becomes 0, 1, 1, 1. Then, we reset the result and sign once more. Now, we process the characters 4, plus, 5, plus, and 2, updating the result step by step as we go. After processing these, the result for this inner expression becomes 11. When we encounter the character, we first add sign asterisk operand to the result, although in this case, the operand is 0, so the result remains 11. We then multiply the result by the last sign popped from the stack and add the last result popped from the stack. This gives us result equals 1 plus 1 by 11 equals 12. After this, the dash character updates the sign to -1. The next character is 3, so we add sign asterisk operand to the result. This gives us result equals 12, 3 equals 9. Finally, when we encounter the character, we again use the stack to restore the context. Multiplying by the last sign and adding the last result gives us result equals 0 plus 1 by 9 equals 9. Finally, we process the expression 6 plus 8 within the input string. Just like before, we accumulate the operands and update the result step by step. After processing this part of the expression, the result becomes 23. This is the correct final output for the entire input expression open parenthesis 1 plus open parenthesis 4 plus 5 plus 2 close parenthesis minus 3 close parenthesis plus open parenthesis 6 plus 8 close parenthesis. The time complexity of this solution is O(n), where n represents the length of the input string. This is primarily due to the fact that the algorithm processes each character of the string exactly once using a single for loop. Each character is visited only one time, contributing O(n) to the time complexity. Additionally, stack operations play an important role. When we encounter parentheses, the algorithm performs append operations for opening parentheses and pop operations for closing parentheses. Since both append and pop are constant time operations, O(1), and the total number of operations corresponds to the number of parentheses, this also contributes at most O(n). Arithmetic operations like addition and subtraction are also constant time, O(1), and because these are performed once per operand, they contribute O(n) in total. When we combine all these factors, the single traversal through the string dominates, resulting in an overall time complexity of O(n). Now, let's consider the space complexity of the solution, which is O(n) in the worst case. This primarily comes from the stack usage. The stack is used to store intermediate results and signs whenever a parenthesis is encountered. In the worst-case scenario, if the input string contains deeply nested parentheses, the size of the stack will grow proportional to the nesting depth. The maximum possible depth of nesting corresponds to the length of the string, which is O(n). Besides the stack, other variables like the operand, result, and sign require only constant space, O(1). Thus, the overall space complexity is dominated by the stack usage, which in the worst case is O(n). To better understand the efficiency of this approach, let's compare it to a brute force or naive approach. A naive method for evaluating arithmetic expressions might involve parsing substrings of numbers and recursively solving sub-expressions inside parentheses. This would require string slicing, which has a cost of OK for each slice, where k is the length of the substring. As a result, in the worst case, the time complexity of the naive approach would balloon to O(n squared). In contrast, the optimized solution we're discussing avoids expensive string slicing altogether. By processing the string in a single pass and using a stack to handle intermediate results, it reduces the time complexity to O(n), which is significantly more efficient than the O(n squared) of the naive approach. Now let's break down the best, average, and worst-case scenarios. In the best case, the input contains no parentheses, just digits and operators. Here, the algorithm processes the string in a single pass, resulting in O(n) time and O(1) space since no stack operations are needed. In the average case, where there are moderately nested parentheses, the algorithm still maintains O(n) time complexity. However, the space complexity depends on the nesting depth, which we denote as k. Since k is always less than or equal to n, the space complexity becomes OK. Finally, in the worst case, where the input has maximum nesting depth, fully nested parentheses, the time complexity remains O(n), but the space complexity reaches O(n) due to the stack size. From a mathematical perspective, each character is processed once in a loop, contributing O(n). Stack operations like push and pop are constant time, and since they occur at most n times, they contribute O(n). Arithmetic operations are also constant per character, adding another O(n). When we combine all contributions, the final time complexity is O(n), and the space complexity is O(n) due to the stack. In this section, we'll discuss some common mistakes that can trip you up when solving the basic calculator problem. First, let's talk about ignoring whitespaces. Many assume the input string doesn't contain spaces, but the problem explicitly allows spaces, like in 1 + 1 or 3 to 2. Failing to account for this can lead to parsing errors, so make sure your solution either pre-processes the string to remove spaces or handles them during parsing. Next, we have incorrect operator precedence. Some mistakenly treat plus and dash as having higher precedence than parentheses, but parentheses always take priority. For instance, in open parenthesis 1 + 2 close parenthesis -3, the addition inside the parentheses must be evaluated first. Lastly, handling nested parentheses can be tricky. Without properly managing them, you risk evaluating expressions out of order. Nested parentheses require a stack-based approach, where you resolve the innermost expressions first. For example, in open parenthesis 1 + open parenthesis 2 -3 close parenthesis, you must evaluate 2 to 3 before adding 1. These are some common pitfalls to watch out for when solving this problem. Now let's look at two more common mistakes. The first is overflowing the stack with large inputs. If you rely on a recursive approach, deeply nested or very large inputs could exceed your system's recursion depth, leading to stack overflow. To avoid this, iterative stack-based solutions are recommended, as they're more robust for handling such cases. Another mistake is mixing digits with operators incorrectly. For example, failing to interpret multi-digit numbers or not recognizing that -123 represents a negative number, not subtraction followed by 123. Misinterpreting such input can cause incorrect results. Always ensure that your solution handles multi-digit numbers and correctly associates the minus sign with numbers where needed. By being cautious of these issues, you can create a more reliable and accurate implementation. Next, let's focus on insights that are particularly useful for interviews. This problem is a great example of stack-based parsing, a fundamental technique that's also applicable in recursion, tree traversal, and expression evaluation. When discussing your solution, be prepared to address edge cases such as empty strings, strings with only parentheses, or unusual inputs like 1-, -1, or 123. These can help you demonstrate a thorough understanding of the problem. Time complexity is another key discussion point. Iterative solutions that process the string in a single pass, achieving O(n) complexity, are preferred over naive recursive solutions. You should also be ready to explain trade-offs. For instance, stack-based solutions are more robust than recursive ones for deeply nested inputs, as they avoid stack overflow. Finally, this problem ties into several related LeetCode problems, like number 227, which adds multiplication and division, or number 772, which introduces exponentiation and more complex operations. Understanding these connections can showcase your ability to generalize concepts across problems. Lastly, let's explore some alternative approaches and their trade-offs. One option is recursive parsing, where you evaluate expressions within parentheses first. While this method is intuitive and easy to follow, it has limitations, such as stack overflow when dealing with deeply nested inputs. Another approach is iterative stack-based parsing. Here, you use a stack to explicitly handle operators and parentheses. This method is more robust, especially for large or deeply nested inputs, but its implementation can be more complex. A third option is the two-pass approach, where you pre-process the string to simplify parentheses before evaluating the expression. While this can make the logic easier for certain edge cases, it's less efficient due to multiple passes over the input. Each of these approaches has its strengths and weaknesses, so it's important to choose the one that best fits the problem constraints and input characteristics. To wrap up, we reviewed a stack-based approach to solve the basic calculator problem, focusing on efficiency and edge cases. This problem is a great example of how stacks can simplify parsing tasks. Remember to practice similar problems to solidify your understanding. Thank you for joining me, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!